All right, so, I'm happy to see you all. Thanks to those of you who came on Wednesday and Zoom. I appreciated, the people who spoke out and, made comments. I was sitting alone in a room and I'm just like, I go sit here. And I'm really good at talking to myself, but anyhow, what I want to do in terms of, just the start of class, I sent the class an email yesterday. I do that every Thursday, that there's something to be said. And so please be sure you check your email at some point. That's super important. The other thing that I would like to say is that your online homework for lesson 3 is due next Tuesday by midnight. So please be sure you get that worked on. And hey, those of you on Zoom, can you now see my Moodle page?
Yes.
Okay, cool. Sometimes I have to like stop sharing and then reshare. Sometimes it works. So thank you very much for telling me. So the other announcement that I made, yeah. Yeah, you'll see that it was, when people email it to me, I just put it in the grade book. Yeah, so check your grade book on Moodle. Yeah. Thank you. So this was announced in class on Wednesday, but just to point out a couple of things. On your class Moodle page, like right when you jump in, this is a document right here that you don't do any computations with, but it just helps you tell the difference between when to use the multiplication principle and when to use combinations. You're not required to do this, but it's there for your practice in case you want additional practice. This is just one document. It's the solutions are at the end. Okay, so you can check your answer. This here is more combination practice. This gets pretty in depth. This is not, neither of these are for a grade. You'll see that the solutions are posted here. If you're going to do these for extra practice, I would strongly recommend you do not look at the solutions until you've attempted everything, okay? Because when you look at the solutions, you know what to work toward. And if only life was that way, right? Unfortunately, it's not. So again, this isn't required. I just like to give you opportunities for practice and urge you to take advantage of that. So if you go to the class activities on the Moodle page, you will see that there's one class activity 2. I posted the solutions after class on Wednesday. Please get them into me on time because once I post the solutions, that's that. Okay. Again, I do drop the 2 low activity scores. So if you miss 2 activities or just don't do well on them, you know, that's certainly not going to hurt you. But you'll notice that I posted class activity 3. I do have hard copies here for those of you who want to pick up a hard copy. Otherwise, this is a Word document that those of you who are zooming in can get. Anyone who's here today, I have all the lab activities 1 and 2. So if you physically handed it in to me, I have it to hand back to you. If you haven't noticed, I like to get things graded immediately. You know, if I have the expectation that you're going to do your work in a certain time period, I think it's only fair that I get my feedback back to you within a respectable time period. So you'll see your grade in the Moodle page. So if you email me your class activities, I don't print them out. That's just to save trees. But I still get it and record you. Okay. So, any questions? Activity 3 will be due next Wednesday. Next Wednesday at class time at the latest. You can give it to me whenever. Thank you. Any other questions? All right, now that more people are here, do you have good weekend plans? Of course. Are you doing homecoming? I just learned it was homecoming. I'm a little behind the times. Oh, cool. Where do they live? Nice. Are you excited? I love it. You know, all I had to do was hear the change in the tone of your voice. Yeah. Yes, they're your parents, but I was happy for you. Right? Totally. You should be. Yeah. Anyone else have good plans? Well, it's a couple days that you don't have the same schedule. Perhaps you work all weekend, in which case you're on a schedule, but at least it's slightly different. All right. Well, I would like to jump back into the material. I'm really happy to be here. I'm just saying, I had a good trip to Billings and it went fine, but I like being home and yeah, so, and I like talking about math. All right. So, attendance was somewhat sparse on Wednesday on Zoom. So my hope is if you weren't able to attend that you've accessed the video. You know, however you get it, again, I don't make judgments. I just want to be sure that you're getting the information and keeping up with what's going on in class. So we got to talk a bit about starting probability. And we talked about different forms of probability, the experimental, subjective, and theoretical. Again, we're pretending that we live in a vacuum in a perfect world. And so that there's equally likely outcomes. Okay. So we then brought it down to the fact that we would run different quote unquote experiments. That's just anything with an observable result. And within those experiments, then we would talk about the sample space, which is the set of all possible outcomes. Okay. And we went through a few experiments where we listed the sample spaces as well as a couple different events, which are the particular subset of the sample space. At this point, I want you to think of your sample space as the universe. Okay. And that changes in the context of each problem. But I think that that's a really useful way to view that sort of thing. So what I'm going to say is as follows. Well, I'm just going to start out with a really rockin' definition. How does that sound? Oh, yeah. All right. For a sample space S with equally likely outcomes, that, my friends, is the key. Okay, we're assuming that every die is fair, every coin is fair. It's not really the case. Okay, but we're assuming that the probability of an event I'll call my event E, again, due to my lack of originality, is, okay, when you write P of E, what I'm saying is that's the probability of E. And it's equal to the number of elements in the event divided by the number of elements in the sample space, provided that the number of elements in the sample space is non-zero. Okay, it's illegal to divide by zero. So. Now, I know this is a lot of notation, but this is notation that we've used. Again, this is a way of saying that it's the probability of this event. You're going to see this everywhere from here on out. And it's the number of elements in the event divided by the number of elements in the sample space. Okay. My hope is that you know that I'm going to go through a ton of examples, right? So
can you repeat that?
Yeah, the probability of event E is the number of elements in E divided by the number of elements in the sample space. We talked about this notation, I think, in section 1.2 or lesson 2, I mean. Okay, now something that I'm going to tell you is that when you're talking about the probability of an event happening, it's always got to be between 0 and 1. If you do a computation and you get the probability to be greater than 1, you made a mistake. Okay, if you do a computation and you get the probability to be negative, in other words, less than 0, you also made a mistake. Okay, now I'm going to show you why this is true. You're not responsible for showing me why it's true, but I want to at least prove it to you so that you trust me. Okay, so let's talk about, notice that the probability is just a fraction. Okay, and typically we'll write these in fraction form or decimal form. There are times that we'll put it in percent form. Okay, unless you're told specifically to put it in a particular form. I'm not particular myself. So, but online homework can sometimes be a little pickier. So why is the probability always between 0 and 1? Well, what we're saying here is that the smallest it can be is 0. But let's talk about what is the smallest an event can be. And you'll recall we listed some events on Wednesday. So for example, when we were talking about rolling a fair die, and we talked about the event of rolling a number greater than 9. What was in that event? Nothing. So the smallest an event can be is the empty set, right? Nothing. And I think you'll grant me that the number of elements in the empty set is 0. There's nothing in there. Okay. And you don't have to write this down necessarily, but I want to show you how this works. So we could say, well, the probability that you get the empty set is the number of elements in the empty set divided by the number of elements in the sample space. We know that there's nothing in the empty set, and we could care less how many are in the sample space, because what is 0 divided by any number? 0. Therefore, the smallest a probability can be is 0. Now, let's talk about why the largest a probability can be is 1. Well, what's the largest possible event that we could have given a sample space S? Isn't it just our entire sample space? Right? Remember, your sample space is the set of all possible outcomes. So the largest an event could be is all of that. Okay, so I claim that the largest an event can be is the actual sample space. Well, using this formula up here, the probability of the sample space is the number of elements in the sample space divided by the number of elements in the sample space. And what is any number divided by itself equal to? 1. Now, you're not responsible for proving this to me, but I think it's very important that you see why the probability has to be between 0 and 1. You cool? Oh, yeah. Okay. So the next thing that I want to say is as follows. Suppose this whole thing is my universe or my sample space. And suppose this is my set E. Okay, I don't really care what E is. Cool. Do you agree that E complement is everything outside of E? Right? The complement. This is where everything that we're doing now builds upon the previous. Okay, this is why I always say don't fall behind, because I'm assuming some familiarity. Okay, so remember E complement is everything in the universe except E. Would you grant me that E union E complement is my sample space? Because it makes up my entire universe. Right? Union is put them together. This plus this is everything. Well, then the probability of E union E complement, since they're equal, is equal to the probability of the sample space. And what is the probability of the entire sample space? 1. You're doing great. Okay. Well, these things are disjoint sets. So we can say then that the probability of E plus the probability of E complement is 1. Which leads us to say, and we're not going to use this that often, but it is going to be helpful in terms of computations. Do you agree I can move this term to the other side? Because I'm adding it here. How do you move this to the other side? You subtract it from both sides. Now you might ask, why are you doing that? Reasonable question. What this gives you is that the probability of an event is 1 minus the probability of the complement of that event. Now, why do we care about that? Because sometimes it's a total pain in the rear to compute the probability of an event, but you already are aware of what the probability of the complement of that event is. So this is another technique that we can use in order to find probabilities. And I'll show you that moving forward. All right. So at this point, what I'm going to do is I'm going to start playing with a bunch of different examples. Now, what I want to say is as follows. I'm going to start out by doing a few examples using a deck of cards. As I mentioned in class on Wednesday, there will not be a test question that involves a deck of cards, because I don't assume that everybody is really familiar with playing cards. There are questions that I like to do in class, and there's also questions that are on your online homework that involve cards. But I differentiate between what's a test question, because if you're still kind of trying to figure out how a deck of cards works, it's not really a very fair test question, okay? But I went through a deck of cards last time, and you just have those notes in front of you. Okay. So now we're just gonna play, and we're gonna start playing where things are relatively speaking straightforward, and we'll get funkier as we move along. Okay, but all good things and all good time. Okay, so suppose I have a standard deck of 52 cards, and assume we select one card at random. What is the probability of drawing a 6? Well, using our formula, it's the number of ways to pick a 6 divided by the total number of options. I won't always write this out, but certainly as we're just learning this terminology, I think it's really helpful. Well, how many 6s are in my deck of cards? 4 of them. How many cards are in my deck of cards? 52. Not that I would ask a card question on a test, but as far as I'm concerned on a test, that could be your final answer. Okay, your online homework wants you to simplify your fractions. They're picky. On the test, I do not ask you to simplify fractions. You're more than welcome to. But again, tests are timed experiences, and I have to think very mindfully about how I want you to be spending your time. But, and I'm not going to go detailed into fractions here. If anyone needs extra assistance, I can point you to that. But what you could say is the numerator is 1 times 4, the denominator is 13 times 4. You're multiplying, you can cancel those 4s, and so you get 113. This would be totally cool for me on a test or the activity, anything you hand in to me. But on your online homework, you're going to want to simplify. Any questions this far? Yeah. They most likely will. And one other comment that I want to make, and this is so important, so thank you so much for asking. When you are doing your online homework, number one, if you think your answer is correct, but you're being marked wrong, hit message instructor. Online homework can get very particular sometimes if you enter a decimal and they wanted a fraction. I'm totally down with going in and giving you full credit, okay? Number two, sometimes the online homework will say enter it to 4 decimal places. But if you make a rounding error or by accident you enter it 3 decimal places, they're gonna mark you wrong. Hit message instructor. I'm totally down with going in and giving you credit. Like, it's a nothing thing for me, so please. And if you think you're right, but I look in and see that you're not right, I will show you the correct way of doing it. Okay? Don't be shy with the message instructor thing. Like, I love nothing more than helping people with the math. All right, let's do some more cards. What is the probability of drawing a black 9? Well, how many black 9s are in my deck of cards? 2. How many cards are in my deck of cards? 52. Again, as far as I'm concerned, that's cool. You can leave it that way. If you simplify it, you get 126. What is the probability of drawing a heart? Well, again, if you're not familiar with cards, go back and look at the sheet where we talked about the suits. How many hearts are in your deck of cards? There are 13 hearts out of a total of 52. And if you simplified it, you'd get 1/4. What's the probability of drawing a 2 or a 4? Well, how many cards are 2s or 4s? 8, right? There's 4 2s and 4 4s. So we have a total of 8 out of 52. Now, what if I said, what is the probability of drawing a 2 and a 4? We're only picking one card. 0. There are no cards that are both 2s and 4s. Again, I'm only doing this example to contrast and to remind you of the differences between the words for and. Are you thrilled? Awesome. All right. So suppose now we're going to talk about candy. One jelly bean is selected at random from a jar containing 3 white ones, 4 orange ones, 5 yellow, and 8 black. Now with M&Ms, the color doesn't matter. They all taste the same. With jelly beans, we're talking something totally different. I love black licorice, so okay. Anyway, we're only picking one jelly bean. So what if I want you to find the probability that, part A, it is white. Notation wise, we'd say P of W. Well, how many ways can we pick a white jelly bean? 3, because there's 3 white jelly beans. Out of how many jelly beans are in my jar? There's 20. Any questions on where we got the 20? If you have it, ask. Don't settle for not understanding here. Okay, what is the probability that it's orange or yellow? Well, how many jelly beans are orange or yellow? 9 out of 20. What is the probability that the jelly bean is not black? Good. 12 out of 20. Remember, not black just means cover that possibility up, and everything else is a possibility. You with me there? Okay. I'm going to still talk about jelly beans, but I'm going to start introducing something else along with it. And we are going to get deeper here, okay? But I just really want to lay the groundwork here. So suppose a jelly bean is selected and it's orange. Hooray. Okay. If it is replaced, in other words, put back in the jar, find the probability the next jelly bean is orange. Now, if this seems like a stupid question for me to ask, maybe when we do the other part, it'll seem a little clearer. Okay, so what happened? I had a jar of jelly beans. I picked a jelly bean. I looked at it. I'm like, oh boy, this is an orange jelly bean. I put the jelly bean back, and then I go and I pick a jelly bean out of the jar. What's the probability that that next jelly bean is orange? I heard someone say it. Same, right? We put it back, so there's still 4 orange jelly beans in the jar, and there's still 20 jelly beans in that jar. Yeah? Right, we're just picking one. Yes, but check this out. So suppose a jelly bean is selected and it's orange. So I eat it. Find the probability that the next jelly bean I pick is orange. Any questions on the scenario of what we're playing with? So I pick one out, it's orange, I eat it. Now I pick another one out. What's the probability that the next jelly bean is orange? Well, how many orange jelly beans are left in the jar? 3 out of a total of how many jelly beans? 19. You with me there? So what am I getting at? I'm getting at there's a difference between when you replace it versus not replace it. Are there questions so far? Okay. Let me do an example that looks a little bit different. Suppose we're talking about people's favorite hobbies. I don't know, suppose skiing. How many people think skiing's their favorite hobby? Just give me 5? Okay. How about reading? Thanks. We can get into double digits too, by the way. Okay, how about drawing? 12. How about doing math? Okay, tell me one other hobby. What do you like to do? What is it? I love it. How many people like gardening? All right, as you know, this was a scientific study. Okay, so suppose a person from this group is selected at random. Find the probability that, I'm going to call this S, I'll call this R, I'll call this D, I'll call this M, and I'll call this G. Find the probability that the person likes to draw. In other words, P of D. How many people here like to draw? There's 12. Divided by what? It's 71. Okay. Yeah, you want to add this. Oh, this is so cute. 50, 71. I love it. I love it when numbers are nice with each other. Any questions? Okay. How about the person doesn't like to read? It's 70 out of 71. You could write that as the probability of our complement, right? Not read is the complement. Now, I would venture to say that maybe you didn't actually take the formula per se, but I would venture to say that you probably answered it by doing this computation. Okay. In other words, instead of covering up the readers and adding everybody else, what you probably thought to yourself is, well, it's everyone but this one person. Okay. So I claim if you did it that way, you were actually using this without necessarily making that formal connection. Now, why am I showing this to you that way? Again, I'm showing you this because you're going to see things in a table. All right, now it's going to get so cute. I'm going to go back to cards for a sec. What if I ask, what is the probability of drawing a face card or a black card? I can call this F and this B if I would like to. We've put the word or with the operation plus. How many face cards are there? There's 12 face cards. How many black cards are there? 26.
Oh.
There's 13 of a particular suit though. So got a good number. Can I just add these numbers together and say, well, it's 38 out of 52? Exactly. You can't just add these together because you don't want to double count. So what I want to remind you of is a formula that we saw previously. We saw, do you agree or means union? Remember we had the union rule that the number of elements in the union of two sets is the number in the first plus the number in the second minus the number of elements in the intersection. Remember we talked about this? And again, the reason why is because, oops, if you want to talk about the union, that's these three regions. If you take the number in A, that's this and this. If you take the number in B, that's this and this. But notice we double counted these, so that's why you subtract that off. So for probabilities, we have a similar formula. Again, you don't have to memorize formulas because you get a sheet of paper with notes on your test, but you do need to know when and how to use them. We say that the probability of the union of two events is the probability of the first event plus the probability of the second event minus the probability of the intersection. Do you see how this follows from the union rule that we played with? Okay. So going back to this example, we could say we want to find the probability of F union B. And using this formula, it's the probability of the first plus the probability of the second minus the probability of the intersection. How many face cards are in my deck of cards? 12. So 12 out of 52. How many black cards are in my deck of cards? 26 out of 52. And how many of those black cards are also face cards? 6 of them, half of them. So you get 32 out of 52. I have 2 more quick examples to do. Are there questions here? What's the probability of drawing a heart or a queen? Well, I could say it's the probability of drawing a heart plus the probability of drawing a queen minus the probability of the intersection. How many hearts are in my deck of cards? 13. There's 13 of any suit. How many queens are in my deck of cards? 4. And how many queens of hearts are in my deck of cards? Right? H intersect Q means it's a queen of hearts. There's 1. You okay? Okay. So we get 16 out of 52. What if I want us to find the probability of drawing a heart or a spade? This is the last example of the day. So just be, because next time we're going to go back to Venn diagram. Aren't you excited for Monday already? Okay. How about a heart or a spade? Well, we could say it's the probability of drawing a heart plus the probability of drawing a spade minus the probability of the intersection of the 2. What's the probability of drawing a heart? 13 out of 52. What's the probability of drawing a spade? 13 out of 52. How many cards are hearts and spades at the same time? None. So you get 26 out of 52. Is this okay so far? Oh, fantastic. Well, I hope you all have a super duper awesome weekend. If you are here and want a paperback, you just got to tell me your last name.